having me here and for the opportunity to share my idea in this setting. The work that I'm going to present is a joint work with Michele Pezzoni and Renilde Wegeler who is here. In defense of the organizer, I have to say that they did a good job also, not only in combining paper and discussant, but also in combining paper in the same section. Because over the presentation, you will see some curves, some graphs that are the same shared by Shane this morning. When we received the call for this conference, my co-author and I said, well, more than a paper, we have a project that is fitting the conference. So today, in the next 20 minutes, I will do my best to share with you our ideas and the findings of this project. The common idea is to explore heterogeneity in trajectories of novel technology over time and space. So the two main ideas and the two main questions that we have in mind is how fast is new technology going to be a hit, and how far is a new technology going. And the inspiring work by Griliches was his paper 1957. And here I'm reporting a different quote with respect to Shane this morning. By concentrating on a single measure, well-defined and reasonable, well-recorded development, hybrid corn, we might hope to learn something about the ways in which technological change is generating and propagating in U.S. agriculture. With this idea and inspiration in mind, our aim in the project is to identify on a large scale novel technology and their trajectory to learn what explains heterogeneity in trajectories. On tracing technological trajectory, so far we have few case studies on single industrial application. So starting from the work of Griliches on hybrid corn, other work follow on investigating specific industrial application. So for instance, we have Achilles on antibacterial drugs, Verspagen on fuel cell, and later Songs and co-author on hybrid electric vehicles. But until now, there are no empirical studies that reconstructed the trajectory on a large pool of technology, and that has explained differences across curves. So our idea here is, first of all, to identify a large pool of novel technologies when they appear, so their origin. And once we have identified those technologies, we want to map the technological trajectory of all these technologies. Having this large pool of technologies allow us to analyze what are the factors explaining differences across technologies over time and space. So let's start with our result about heterogeneity in trajectories of novel technology over time. So the main research questions here are, why do some trajectories take a long time to take off while others take off very quickly? And similarly, why do some trajectories generate a large number of follow-on inventions while others only a few? And here, in this graph, we can see the heterogeneity across technological trajectory. This is the plot of our sample. First of all, the first step was to identify novel technology. And here, the idea is to identify the origin of a novel technology when a novel invention appears. And here, the idea is also to consider and to adopt a recombinatorial definition of novelty. So for us, the invention is novel when, for the first time, we observe in that invention a new combination, a novel combination of pre-existing technological components. Once the origin of the technological trajectory has been identified, the second step was to map the trajectory. And in order to do that, we follow on invention that reuse the novel technology. And here we borrow the idea from Arthur, and the idea that each technology has a backbone that remains stable over time. And for us, the backbone that stays stable over time is the new combination of technological components that we observed. Here some remarks. Differently from Griliches and the case of hybrid corn, we do not consider pure adoption, but we consider, we measure and we trace the technological trajectory looking at follow-on invention. And the second remark is that we trace reuses. We do not reconstruct trajectory, consider citation. And some of the work from Adam, for instance, claim that citation correlate, but are poorly, sometimes poorly with reuse. And in our study, we assume that novel technology follow novel technology basically follow a specific path. And in particular, those novel technology have first moment of takeoff. So basically, inventors need time to learn and familiarize themselves with the technology. And then, slowly, they start to reuse more and more the technology. Until when the technology has saturated the potential and basically the technological impact has been reached. So we measure, first of all, the takeoff as the number of years elapsed to reach 10% of the technological impact. In taking this 10%, again, we got inspiration by the work of Griliches. We tried also different thresholds, and our results are stable. Then the technological impact for us is the observed cumulative number of inventions after 20 years. However, some technologies take a long time to reach their technological impact. They do not reach their technological impact within the space of 20 years. So basically what we have done is to use the observed cumulative distribution of follow-on invention to fit a trend function that allows us to estimate the technological impact at an infinite time. And the curve that did for us the best fitting is an S-curve. And this S-curve will fit the evolution of our technology. But most importantly, those curves, they have appealing mathematical property. And in particular, they can, each shape, their shape, can be represented only by three parameters. The ceiling, the midpoint, that is the 50% of the ceiling, and the alpha parameter, that is the steepness of the slope at the midpoint. This property for us is particularly important because in the exercise that we will see during the presentation, basically then we will focus on takeoff and technological impact. Just to give you an idea of how we operationalized our concept, here I'm reporting the case of the transgenic mammal technology. This technology appeared for the first time in 1985, when the oncomouse, so the mouse that is known and is used in labs to study cancer, appeared. And here we can see the first page of the invention. And basically what we did was to look at the IPC code that for us are the technological component. And in this patent, we observe for the first time two new technological components that combine together for the first time. Which are those components? Those components are the genome editing and rearing mammal from fertilized mouse eggs. So this is the first step. So in 1995, when the oncomouse appeared, we trace the origin of the technology. And then we reconstruct the cumulated distribution of follow-on patents. Looking at all patents that used the same technological component. For instance, in 1996, we see the diabetic mouse using the same component. And then the last step was the fitting of the curve, as we can see in this graph. We did the same exercise considering all EPO patents between 1978 and 2015. And we end up tracing about 11,000 novel technologies that we follow over time. Interesting enough, the S-curve shape is the ideal curve that fit well our technological trajectory. And more importantly, we observe a lot of heterogeneity across curve. In particular, we can see here the heterogeneity in terms of takeoff and in terms of technological impact. If we look at this number, we see that the average technological impact corresponds to about 60 patents. But there are also technologies that reach more than 1,000 of reuses. The case of the oncomouse, for instance, is the mammal transgenic technology is a technology with a high impact because the impact is much higher than the average and a long takeoff time, about 9 years, compared to an average of 5 years. So, a lot of heterogeneity across curves. But how can we explain that heterogeneity? And here, our exercise. Basically, we consider the trajectory features, and in particular, the takeoff time and the impact as a function of the component characteristics and some controls that related both to the inventors and to the applicant characteristics. In terms of in searching for which factor shape the technology, in terms of characteristic of the combined component, we consider if the components recombined together were similar or familiar to the inventors, with the assumption that if the two components combined together are similar or there is a high familiarity within the community of the inventors with these two components, the resulting technology will have a short takeoff time because the resulting technology is relatively simple, so easy to understand. But at the same time, there will be a cost in terms of technological impact, because the technological impact will be low. On the contrary, if you combine together components with a high science base, The resulting technology will take longer to take off because it will be relatively complex, and so the engineer, the inventors need to be trained, but there will be a gain in terms of technological impact, because science usually allow to generate technology that are abstract and general, so with a higher frequency of reuses. The main finding is that while the ideal technology is a technology that take a short time to reach, to be reused, and at the same time have a high technological impact, this is not possible. So usually there is a trade-off. And the example is the mammal technology. The mammal technology is a so-called risky technology because it combines this similar component, it has a high science-based content, and there was a lower familiarity with the component at the beginning. This technology is a technology with a really high technological impact, but this technological impact came at the cost of a long take-off time. So, what in terms of policy implication, which are these policy implications? The idea is to try to stimulate this complex technology to speed up, especially in the early phases. And here is where policymaker can intervene to speed up the process of evolution of those kind of technology. So this is our general framework. And we think that this framework has a great potential, and there is a lot to do with this framework. And so far, as a follow-up, we have started to investigate the geographical dimension. And here, some finding about heterogeneity in trajectory over space. So, having identified those technological trajectory, basically what we wanted to observe is how invention related to the technological trajectory jump. And so basically we order patent chronologically according to their application date within the technological trajectory. We geolocalize inventors using the database of Gaetan, who is here, and Morrison. And then the idea is to see how reuses jumps in space. So if, let's say, the oncomouse developed in 85, where is going the next invention that use the same component? And the idea is that the geographical coverage of a technology I expand each time inventors of a patent S bring the technology to a new place. So the idea is to consider the jump length. If the jump length is big enough, and there can be, we can observe the generation of a new cluster. And we consider the probability of generating a new cluster when the jump is greater than 1,000 kilometers. That for us corresponds to the 19th percentile of the distribution. So the idea is to understand why do some technology follow an agglomerated developing model and travel short distances while others spread worldwide. Among the several elements that can explain and several factors that can explain this, at now we focus on one particular element that is the science content. And the idea is to understand if technology fly on the wings of science. Again, in our technology, we observe a lot of heterogeneities. So there are technologies that have small jumps and technology with very long jumps. Interesting enough, the length of the jump depends on the phase of evolution of the technology. So technology register a long jump, especially in the take-off time, while in the maturity phase, those jumps are shorter. Again, yes, I will stop. So I will stop jumping on the general conclusion. What we find is that science-based technologies show a diffused development model with longer geographical jumps, while not science-based technology tend to follow a more agglomerated development model. But importantly enough, science give wings to technology to reach longer distance only in the maturity, in the growth and in the maturity phase, while at the beginning those technologies stays concentrated. Just to wrap up, we hope...
You really do need to wrap up.
Yes, I will. This is the last slide, I promise. So to wrap up, in the spirit of Griliches, and here some copyright to Adam, we hope that we have convinced you of the surprising, relevant, and data-driven agenda of studying technological trajectory. A paper and a project is never over, so there is much more to do, and we intend to do more on different fronts to understand what we are measuring. Thank you so much, and sorry if I took longer for the presentation.
Right, thank you very much, Fabiana. Actually, so super interesting. You know, this is a bit of an unusual talk because it combines a few different papers, but actually I think the method is quite interesting because it's a fairly difficult thing to identify in large data. So en masse, you know, is new technological trajectory. So let me tell you why I care about that with the world's like ugliest graph. So you know, despite this being the Zvi conference, and literally everyone here, I'm sure, has read the 57 paper. It's probably the most famous graph in all of the economics of innovation. I think it's underrated how much diffusion matters. Because what I plotted here is the amount of economic surplus created by some innovation. On the y-axis, the extent of use on the x-axis. And this red line here that integrates to 0 is what happens when you invent something. So there's no economic surplus created until something is used, okay? And so what we actually care about is that eventually a thing diffuses across society, either as a single product or through a series of products that are then invented, and that diffusion creates economic surplus. So only studying this part, which is some huge fraction of studies in the economics of innovation, is missing like really important things here. And as Fabiana shows, there's actually a ton of heterogeneity, and the processes underlying what speeds going from here to here up are actually not that well understood. A little better understood for stuff like single products, obviously going back to Zvi's work, and a little bit earlier, as I mentioned. But for technologies as a whole, I think much less understood. So this is not a new point that I'm making. You know, you can go back before Zvi to the former Harvard-based leader of the economics of innovation, our friend Mr. Schumpeter. And Schumpeter says, famously, that invention doesn't necessarily produce innovation. He thinks these are very different things. It produces of itself no economically relevant effect at all. That's that one line that integrates to 0. So Schumpeter already knew this. So let me give you an example of from obviously my favorite industry, the airplane. So of what I mean by this. So here on the left, I assume folks probably know what this picture is, one of the most famous pictures in the history of innovation. We're here at Kitty Hawk, North Carolina. It's 1903. This is the Wright Flyer. Can I borrow a piece of paper from you here, Pierre?
The one that says stop?
That'll work. Perfect. Okay, so this thing is crazy. This plane that I showed you, and let me just fold this up and I'll show you why. Okay, we got to do this. There we go. All right, so, okay. So this plane on the left, it flies for 29 seconds. Why does it fly for 29 seconds? Because basically what they're doing is they need to change the airflow above each wing, and they've just attached ropes to fabric. And so they're going to be sitting there in the middle of the plane, and they're going to pull on the ropes. And as they pull on the ropes, it's just going to change the shape of the wing like this, and that's going to allow them to control the plane. But you might think, I go on planes now, and I hope that the pilot is not doing this. You know, when they say the planes fly by wire, that's not what they mean. So they just mean it flies electronically. So of course they don't fly planes like this. This is an insane way to fly, and it's basically a technological dead end. On the right, this picture, I suspect most people don't know what this is, but maybe since we're in Paris, someone knows what this is. Who is it? Oh, close. Sorry? Santos Dumont. You must be Brazilian. They love Santos Dumont. But no, it's actually Henri Farman. So Henri Farman in 1909. This is the Farman 3. So this plane was the first plane to have a certain feature, which similar to the Wright brothers. I need to change the airflow on top of the wings. But what you'll see in the back of the wings here is I've got these just attached flaps called ailerons. Not a coincidence that word's French. And if you get on your plane and you go back home, and you look out the window when the plane's taking off and landing, you're going to see little metal flaps on the back kind of go up and down, changing the airflow of the wings. So this, now we're starting to get somewhere. So the technological trajectory here, this is a dead end. This is no economic surplus at all. Here we're really starting to get somewhere. And how do I know we're starting to get somewhere? Because Henri Farman and his brother actually in 1919 fly the first non-trivial commercial flight, actually from Paris to London, that you could buy a ticket for. So we eventually somehow need to figure out the economics of how do I get from this thing to the eventual commercially viable products that matter. So how am I supposed to trace those trajectories? We know how to do it for single products, right? You know, I put this in, I didn't know that Shane had the same thing. I thought we can't have the Zvi conference and not see this guy at some point, right? So what we basically for single products, we'll just count the intensive margin of use in the same way that Zvi does. But that doesn't really help with this problem, right? Like it doesn't help me understand what factors led to this particular trajectory. I only need one piece of paper, don't worry, Pierre. So what can we do? I think this is the clever idea that coming from Fabiana and her co-authors is you don't want to just trace through citations for a variety of reasons you already heard about in this conference, but I think this is a really good example. So the Anka mouse, which a lot of you will know from Fiona and Friends' work, this actually combines these two 6-digit IPC codes, rearing and breeding animals and compounds containing 2 or more nucleic acids. Had never been combined before in the same patent. The interesting thing is we wind up seeing 220 patents that combine these 2 IPC codes over the next 20 years. Of those, 6 of them cite the Anka mouse paper. And a full 2/3 of them don't cite a single other paper with that same combination. So there's just no way you're going to use future citations to properly trace out this technological trajectory. But it does not seem unreasonable that you can just look at the series of inventions that follow that just combine these 2, right? And call that the trajectory, and then look at what factors are going to affect how fast or how slow that trajectory takes off. So, as Fabiana mentioned, S-curves fit really nicely, actually, to these trajectories. You do see a kind of slow ramp up, and then that really nice run up on the S-curve, and eventually we kind of plateau out as technologies start to be surpassed by things in the future. So what technologies are kind of slow growing but wind up very big? Science-based technologies, so ones where their combined codes draw on a lot of underlying science, and dissimilar technologies, so ones that are quite far from each other in the IPC classification. Now, one caveat here, I hate to caveat this paper because it's already published, but I do think it's worth mentioning. These regressions don't have nonlinear functional forms, And so we know from like Jones and Ahmadpour, and among others, that I just find it very, very unlikely that extremely dissimilar things on average wind up very big, right? So extremely dissimilar combinations of inventions. I have a few that I've used in my class of like, you know, when you show like the weirdest patents possible in the patent literature, I'm sure many of us do this, those ones don't create trajectories and are of no importance. And we knew this in academic literature as well from prior work, that you have to be like a little bit weird and not a lot weird. I'm not sure, I think Ben might be gone, but when I was a PhD student, he was actually writing this paper, and I was kind of a weird PhD student. And so I had an idea for a paper, and he said, Kevin, you want to be a little bit dissimilar, a little weird, but not that weird. And I can prove it empirically that would be a bad idea. So, okay. And they also travel further in space, which is pretty cool when they're science-based. So I think actually, just to finish up, and I see one slide has taken leave for lunch already. We're already at number 2. So I think this idea of like having trajectories with data this large on the order of like 10,000, there's just a number of questions that I'd like to see answered. And I think you can answer it with this data. Obviously, a little more validation of this measure is probably necessary before we go too far. But for example, this is like a classic one in the economics of innovation is the precision of the thing that I'm covering in my patent. How does that matter for what builds on it? I would suspect that I see slower takeoff with very precise patents because the ability of future inventors to build on my work is more limited, unless, for example, I'm able to license very easily, in which case maybe then I see more. But like this question of what patents are doing to restrain or to encourage future invention on the theory side is something we've thought about quite a bit. Do that. On the theory side, something we've thought about quite a bit, but it's very hard to actually investigate empirically. And so these are the type of things I think you can answer with a little more precision. I've got a few more examples, but just for reasons of time, I want to make sure that Fabiana gets some questions. In any case, play around with this data. It's very cool. Thank you very much.